scale-free network is a network whose degree distribution follows a power law, at least asymptotically. That is, the fraction p, k, of nodes in the network having k connections to other nodes goes for large values of k as. Where is a parameter whose value is typically in the range 2-3, although occasionally it may lie outside these bounds. Many networks are conjectured to be scale-free, including World Wide Web links, biological networks, and social networks, although the scientific community is still discussing these claims as more sophisticated data analysis techniques become available. Preferential attachment and the fitness model have been proposed as mechanisms to explain conjectured power law degree distributions in real networks. History. In studies of the networks of citations between scientific papers, Derek de Sola Price showed in 1965 that the number of links to per person that is, the number of citations they receive via euro had a heavy-tailed distribution following a Pareto distribution or power law, and thus that the citation network is scale-free. He did not however use the term scale-free network, which was not coined until some decades later. In a later paper in 1976, Price also proposed a mechanism to explain the occurrence of power laws in citation networks, which he called cumulative advantage, but which is today more commonly known under the name preferential attachment. Recent interest in scale-free networks started in 1999 with work by Albert Loiszla Barabasi and colleagues at the University of Notre Dame who mapped the topology of a portion of the World Wide Web, finding that some nodes, which they called hubs, had many more connections than others and that the network as a whole had a power law distribution of the number of links connecting to a node. After finding that a few other networks, including some social and biological networks, also had heavy-tailed degree distributions, Barabasi and collaborators coined the term scale-free network to describe the class of networks that exhibit a power law degree distribution. Amaral et al. Showed that most of the real-world networks can be classified into two large categories according to the decay of degree distribution p, k, for large K. Barabasi and Albert proposed a generative mechanism to explain the appearance of power law distributions, which they called preferential attachment, and which is essentially the same as that proposed by Price. Analytic solutions for this mechanism were presented in 2000 by Drogovtsev, Mendes and Samukin and independently by Krapivsky, Redner, and Lievres, and later rigorously proved by mathematician bar copyright La Boloba S. Notably, however, this mechanism only produces a specific subset of networks in the scale-free class, and many alternative mechanisms have been discovered since. The history of scale-free networks also includes some disagreement. On an empirical level, the scale-free nature of several networks has been called into question. For instance, the three brothers Faloutsoos believed that the Internet had a power law degree distribution on the basis of tracer root data. However, it has been suggested that this is a layer 3 illusion created by routers, which appear as high-degree nodes while concealing the internal layer 2 structure of the ACEs they interconnect. On a theoretical level, refinements to the abstract definition of scale-free have been proposed. For example, Lee et al. Recently offered a potentially more precise scale-free metric. Briefly, let G be a graph with edge set E, and denote the degree of a vertex by. Define. This is maximized when high-degree nodes are connected to other high-degree nodes. Now define. Where Smax is the maximum value of S, H, for H in the set of all graphs with degree distribution identical to G. This gives a metric between 0 and 1, where a graph G with small s, G, is scale-rich, and a graph G with s, G, close to 1 is scale-free. This definition captures the notion of self-similarity implied in the name scale-free. Characteristics. The most notable characteristic in a scale-free network is the relative commonness of vertices with a degree that greatly exceeds the average. The highest degree nodes are often called hubs, and are thought to serve specific purposes in their networks, although this depends greatly on the domain. The scale-free property strongly correlates with the network's robustness to failure. It turns out that the major hubs are closely followed by smaller ones. These smaller hubs, in turn, are followed by other nodes with an even smaller degree and so on. This hierarchy allows for a fault-tolerant behavior. If failures occur at random and the vast majority of nodes are those with small degree, the likelihood that a hub would be affected is almost negligible. Even if a hub failure occurs, the network will generally not lose its connectedness, due to the remaining hubs. On the other hand, if we choose a few major hubs and take them out of the network is turned into a set of rather isolated graphs. Thus, hubs are both a strength and a weakness of scale-free networks. These properties have been studied analytically using percolation theory by Cohen et al. And by Callaway et al. Another important characteristic of scale-free networks is the clustering coefficient distribution, which decreases as the node degree increases. This distribution also follows a power law. This implies that the low-degree nodes belong to very dense subgraphs and those subgraphs are connected to each other through hubs. Consider a social network in which nodes are people and links are acquaintance relationships between people. It is easy to see that people tend to form communities, that is, small groups in which everyone knows everyone. In addition, the members of a community also have a few acquaintance relationships to people outside that community. Some people, however, are connected to a large number of communities. Those people may be considered the hubs responsible for the small world phenomenon. At present, the more specific characteristics of scale-free networks vary with the generative mechanism used to create them. For instance, networks generated by preferential attachment typically place the high-degree vertices in the middle of the network, connecting them together to form a core, with progressively lower-degree nodes making up the regions between the core and the periphery. The random removal of even a large fraction of vertices impacts the overall connectedness of the network very little, suggesting that such topologies could be useful for security, while targeted attacks destroys the connectedness very quickly. Other scale-free networks, which place the high-degree vertices at the periphery, do not exhibit these properties. Similarly, the clustering coefficient of scale-free networks can vary significantly depending on other topological details. A final characteristic concerns the average distance between two vertices in a network. As with most disordered networks, such as the small world network model, this distance is very small relative to a highly ordered network such as a lattice graph. Notably, an uncorrelated power law graph having 2 AAI cubed AA3 will have ultra-small diameter DLNALNAN where n is the number of nodes in the network, as proved by Cohen and Haviland. The diameter of a growing scale-free network might be considered almost constant in practice. Examples: although many real-world networks are thought to be scale-free, the evidence often remains inconclusive, primarily due to the developing awareness of more rigorous data analysis techniques. As such, the scale-free nature of many networks is still being debated by the scientific community. A few examples of networks claimed to be scale-free include social networks, including collaboration networks. Two examples that have been studied extensively are the collaboration of movie actors in films and the co-authorship by mathematicians of papers. Many kinds of computer networks, including the Internet and the web graph of the World Wide Web. Some financial networks such as interbank payment networks, protein-protein interaction networks, semantic networks, airline networks. Scale-free topology has been also found in high-temperature superconductors. The qualities of a high-temperature superconductor are a compound in which electrons obey the laws of quantum physics, and flow in perfect synchrony, without friction appear linked to the fractal arrangements of seemingly random oxygen atoms and lattice distortion. Generative models: these scale-free networks do not arise by chance alone. Erdős and Ra copyright me studied a model of growth for graphs in which, at each step, two nodes are chosen uniformly at random and a link is inserted between them. The properties of these random graphs are different from the properties found in scale-free networks, and therefore a model for this growth process is needed. The mostly widely known generative model for a subset of scale-free networks is Barabasi and Albert's rich-get-richer generative model in which each new web page creates links to existing web pages with a probability distribution which is not uniform, but proportional to the current and degree of web pages. This model was originally discovered by Derek J. de Sola Price in 1965 under the term cumulative advantage, but did not reach popularity until Barabasi rediscovered the results under its current name. According to this process, a page with many in-links will attract more in-links than a regular page. This generates a power law, but the resulting graph differs from the actual web graph in other properties such as the presence of small tightly connected communities. More general models and networks characteristics have been proposed and studied. A somewhat different generative model for web links has been suggested by Pennock et al. They examined communities with interests in a specific topic such as the home pages of universities, public companies, newspapers or scientists, and discarded the major hubs of the web. In this case, the distribution of links was no longer a power law but resembled a normal distribution. Based on these observations, the authors proposed a generative model that mixes preferential attachment with a baseline probability of gaining a link. Another generative model is the copy model studied by Kumar et al., in which new nodes choose an existent node at random and copy a fraction of the links of the existent node. This also generates a power law. Interestingly, the growth of the networks is not a necessary condition for creating a scale-free network. Dangalkov gives examples of generating static scale-free networks. Another possibility is to consider the structure as static and draw a link between vertices according to a particular property of the two vertices involved. Once specified the statistical distribution for these vertices properties, it turns out that in some circumstances also static networks develop scale-free properties. Generalized scale-free model. There has been a burst of activity in the modeling of scale-free complex networks. The recipe of Barabasi and Albert has been followed by several variations and generalizations and the revamping of previous mathematical works. As long as there is a power law distribution in a model, it is a scale-free network, and a model of that network is a scale-free model. Features: many real networks are scale-free networks, which require scale-free models to describe them. There are two ingredients needed to build up a scale-free model: 1. Adding or removing nodes. Usually we concentrate on growing the network, that is adding nodes. 2. Preferential attachment, the probability that new nodes will be connected to the old node. Note that fitness models could work also statically, without changing the number of nodes. Examples: there have been several attempts to generate scale-free network properties. Here are some examples: the Barabasi-Albert model, for example, the first scale-free model, the Barabasi-Albert model, has a linear preferential attachment and adds one new node at every time step. Note: another general feature of unreal networks is that is there is a non-zero probability that a new node attaches to an isolated node. Thus in general has the form, where is the initial attractiveness of the node? Two-level network model. Dangalkov builds a 2L model by adding a second-order preferential attachment. The attractiveness of a node in the 2L model depends not only on the number of nodes linked to it but also on the number of links in each of these nodes, where C is a coefficient between 0 and 1. Nonlinear preferential attachment. The Barabasi-Albert model assumes that the probability that a node attaches to node is proportional to the degree of node. This assumption involves two hypotheses: first, that depends on, in contrast to random graphs in which, and second, that the functional form of is linear in. The precise form of is not necessarily linear, and recent studies have demonstrated that the degree distribution depends strongly on. Krapivsky, Redner, and Lievers demonstrate that the scale-free nature of the network is destroyed for nonlinear preferential attachment. The only case in which the topology of the network is scale-free is that in which the preferential attachment is asymptotically linear, that is, as. In this case the rate equation leads to. This way the exponent of the degree distribution can be tuned to any value between 2 and. Hierarchical network model. There is another kind of scale-free model, which grows according to some patterns, such as the hierarchical network model. The iterative construction leading to a hierarchical network. Starting from a fully connected cluster of 5 nodes, we create 4 identical replicas connecting the peripheral nodes of each cluster to the central node of the original cluster. From this, we get a network of 25 nodes. Repeating the same process, we can create 4 more replicas of the original cluster. The 4 peripheral nodes of each one connect to the central node of the nodes created in the first step. This gives now equals A125, and the process can continue indefinitely. Fitness model: the idea is that the link between 2 vertices is assigned not randomly with a probability p equal for all the couple of vertices. Rather, for every vertex j there is an intrinsic fitness xj, and a link between vertex I and j is created with a probability. Note that the model is both in the case of World Trade Web, but is possible to reconstruct all the properties by using as fitnesses of the country their GDP, and taking hyperbolic geometric graphs. Assuming that a network has an underlying hyperbolic geometry, one can use the framework of spatial networks to generate scale-free degree distributions. This heterogeneous degree distribution then simply reflects the negative curvature and metric properties of the underlying hyperbolic geometry. Scale-free ideal network: in the context of network theory, a scale-free ideal network is a random network with a degree distribution following the scale-free ideal gas density distribution. These networks are able to reproduce city size distributions and electoral results by unraveling the size distribution of social groups with information theory on complex networks when a competitive cluster growth process is applied to the network. In models of scale-free ideal networks, it is possible to demonstrate that Dunbar's number is the cause of the phenomenon known as the 6 degrees of separation. See also, random graph, Adesa-Ra copyright me model, Bose-Einstein condensation, a network theory approach, scale invariance, complex network, web graph, references. Albert R. Baraba Cal Statistical Mechanics of Complex Networks. Reverend Mod. Phys 74, 47 a €97. AR Ziv, condition @/01060996. Bibcode, 2002 of EMP. 74. 47a doi, 10.1103/Rev Mod Phys 74.47 a, Amaral, LAN, Scala, A, Bartholomew, M, Stanley, H.E. Classes of Behavior of Small World Networks. Proc. Natal. Acad. Sci. USA 97, 11149 €52. AR Ziv, condition @/00014558. Bibcode, 2000 PNAS. 9711149a doi, 10.1073/FNAS 200327197. PMCA 17168. PMIDA 11005838 a, Baraba C, Albert Loess ZLA cubed. Linked, how everything is connected to everything else. ISBN A0-452-28439-2 a, Baraba C, Albert Loess ZLA cubed. Benabo, Eric. Scale-free networks. Scientific American 288, 50 €9 doi, 10.1038/Scientific American No 503-60 a, Dan Breyer, Yania Bayam. Topology of Large-Scale Engineering Problem-Solving Networks. Phys. Reverend E69, 016113. Bibcode, 2004 PHRV E69A6113B doi, 10.1103/Phys Rev E69.016113 a, Calderelli G. Scale-Free Networks, Oxford University Press, Oxford. Calderelli G., Capocci de los Rios P., MUA plus or minus OSMA scale-free networks from varying vertex intrinsic fitness. Physical Review Letters 89, 258702. AR Ziv, condition @/02073666. Bibcode, 2002 PHRVL 89Y8702C doi, 10.1103/Phys Rev Let 89.258702. PMIDA 12484927 R. Cohen, K. Iris, D. Ben Avraham and S. Haviland. Resilience of the Internet to Random Breakdowns. Phys. Reverend Let 85, 4626 a Euro 8. ARZIV, condition mat/0007048. Bibcode, 2000 PHRVL 85.4626 CDOI, 10.1103/Viz Rev Let 85.4626 R. Cohen, K. Iris, D. Ben Avraham and S. Haviland. Breakdown of the Internet under intentional attack. Viz. Reverend Let 86, 3682 a Euro 5. ARZIV, condition mat/0010251. Bibcode, 2001 PHRVL 86.3682 CDOI, 10.1103/Viz Rev Let 86.3682. PMIDA 11,328,053 A.F. Rosenfeld, R. Cohen, D. Ben Avraham, S. Haviland. Scale-free networks on lattices. Viz. Reverend Let 89 Dangalkov, C.H. Generation Models for Scale-Free Networks. Physica 338 doi, 10.1016/J Phys. 2004.01.056 Drogovtsev, Mendez, JFF, Samukin, A.N. Structure of Growing Networks, Exact Solution of the Barabbas-Sayar Euro-Alberts Model. Viz. Reverend Let 85, 4633 a Euro 6. ARZIV, condition mat/0004434. Bibcode, 2000 PHRVL 85.4633 DDoI, 10.1103/Viz Rev Let 85.4633. PMIDA 11,082,614 Drogovtsev, SN, Mendez, JFF Evolution of Networks, From Biological Networks to the Internet and www. Oxford University Press. ISBN A0-19-851590-1 Drogovtsev, SN, Goldsev AV, Mendez, JFF Critical Phenomena in Complex Networks. Reverend Mod. Phys 80, 1275. ARZIV, 0705.0010. Bibcode, 2008 RVMP. 80.1275 DDoI, 10.1103/Rev Mod Phys 80.1275 Drogovtsev, SN, Mendez, JFF Evolution of Networks. Advances in Physics 51, 1079 a Euro 1187. ARZIV, condition mat/0106144. Bibcode, 2002 AD 551.1079 DDoI, 10.1080/00018730110112519 Erdős, P. Ra Copyright Me, on the Evolution of Random Graphs 5. Publication of the Mathematical Institute of the Hungarian Academy of Science PPA 17 a Euro 61 a, Falutzous, M, Falutzous, P, Falutzous, C. On Power Law Relationships of the Internet Topology. Comp. Com. Rev 29, 251 doi, 10.1145/316,194.316229 Lee, L., Alderson, D., Tanaka, R., Doyle, J.C., Willinger, W. Towards a Theory of Scale-Free Graphs, Definition, Properties, and Implications. ARZIV, condition mat/0501169 condition mat dis NN. Kumar, R., Raghavan, P., Rajagopalan, S., Sivakumar, D., Tompkins, A., Uppal, E-Stochastic Models for the Web Graph. Proceedings of the 41st Annual Symposium on Foundations of Computer Science. Redondo Beach, California, IEEECS Press PPA 57 a Euro 65 a, Manev R., Manev H. The Meaning of Mammalian Adult Neurogenesis and the Function of Newly Added Neurons, The Small World Network. Med. Hypotheses 64, 114 a Euro 7 doi, 10.1016/J Mai. 2004.05.013. PMIDA 15,533,625 Matlis, Jan. Scale-Free Networks A. Newman, Mark E.J. The structure and function of complex networks. ARZIV, condition @/03035516 condition @StatMech. Pastor Satoras, R., for Spignani, A Evolution and Structure of the Internet, A Statistical Physics Approach. Cambridge University Press. ISBN A0-521-82698-5, Pennock, D.M., Flake, G.W., Lawrence, S., Glover, E.J., Giles, C.L. Winners Don't Take All, Characterizing the Competition for Links on the Web. Proc. Natal. Accord. Sci. USA 99, 5207 €11. Bibcode, 2002 PNAS. 99.5207 doi, 10.1073/FNAS 0320856699. PMCA 122747. PMIDA 16578867. Robb, John. Scale-Free Networks and Terrorism, 2004. Keller, E.F. Revisiting Scale-Free Networks. Bioessays 27, 1060 €8 doi, 10.1002/BIS 20294. PMIDA 16163729. Arnodi, R.N., De Castro, P.A. Complex Network Study of Brazilian Soccer Player. Viz. Reverend E70, 037103. ARZIV, condition @/04099609. Bibcode, 2004 PHRVE 70C71030 doi, 10.1103/Viz Rev E70.037103. Reuven Cohen, Shlomo Havlin. Scale-free networks are ultra-small. Viz. Reverend Let 90, 058701. ARZIV, condition @/02054776. Bibcode, 2003 PHRVL 90E8701C doi, 10.1103/Viz Rev Let 90.058701. PMIDA 12633404. External links, SN Graph optimal software to manage scale-free networks. The ERDA's web graph server describing the hyperlink structure of a weekly updated, constantly increasing portion of the www.